All right, welcome back. In the last video for this section, we talked about the divergence test, and in this one, we're going to talk about another test called the integral test. So let's go ahead and see what's going on here. It says in the integral test, suppose that our infinite series, a sub n, is a series with positive terms, a sub n. So that's important. It's got to have all positive terms. Suppose that there exists a function f and a positive integer n such that the following three conditions are satisfied. First, our function has to be continuous. Second, our function has to be decreasing. And I'm going to make a little bit of a note about that in just a second. And then the last thing is we got to have our a sub n from the series. We need to let that be the function that we're taking the integral of, right? This is our function. Let's go ahead and make one note here before we look at an example. So we can say that our function, let's call it f of n, can be eventually decreasing. So it doesn't have to be decreasing right at the beginning, but eventually decreasing. So for example, let's say we have something like this. Say at first the terms start to increase, then they start to fall back and get smaller and smaller and smaller. So a sequence like this is an example of one that even though it increases at the beginning, it's eventually decreasing. I could also give you a visual picture of what that looks like. So say we graph that f of n and it looks something like this. So it starts out as increasing and then it starts to decrease. Okay, so that's another example. All right, so the last thing about theorem 5.9 is it says that if all these conditions are met, so it's got positive terms, it's continuous, it's decreasing, we let our function be a sub n. If all that's true, then either both the series and the integral converge, or they either both converge or they both diverge. So basically, we're just looking to see if the integral converges or diverges, and we know how to do that already because we did that back in section 3.7. And we did that when we did improper integrals. So here we go, example 2. Let's start by letting our function be 1 over x times the natural log of x. That's what we need to do first, and then we need to check our requirements. So first requirement, is f continuous on our interval? And what's our interval? Well, this sum goes from 2 to infinity. So we're going to say, okay, from 2 to infinity. That's the first thing. Second requirement, are all terms positive on 2 to infinity? Okay, that has to be true. And then the last one, we want to know, is f decreasing or eventually decreasing on 2 to infinity? All right, so those are our questions. Now, probably the easiest way to address these questions is to look at the graph of this function. If you know stuff about algebra, we can talk about that as well. But one reason why this sum has to go from 2 to infinity is because if you plug 0 into the function, you get 1 over 0. And also if you plug 1 into the function, you get 1 over 0 because the natural log of 1 is 0, which makes it discontinuous. So let's go ahead, though, and look at Desmos. So our function is 1 over x times the natural log of x. You'll see that at 1, at x equals 1, we have a vertical asymptote. At x equals 0, we also have a vertical asymptote. That's because of, as I said earlier, when you plug in 0 and 1, you get division by 0. Okay, so let's see if all those things are true. The first thing, is our function continuous from 2 to infinity? Well, look at this thing. Yeah, it's definitely, there's no holes, right? It was discontinuous at 0 and 1, but from 2 to infinity, it's fine. Are all terms positive on 2 to infinity? Well, there are negative terms down here between 0 and 1, but after 2, look, everything's above the x-axis, so everything's positive. And is it decreasing? Well, yeah. After 2, it looks like it's going down towards 0, right? So all three things do hold for this problem. We got, is that continuous? Yes. Are all the terms positive? Yes. Is it decreasing? Yes. So the integral test applies. And now we just need to find the integral. So let's do that. So we have this improper integral. We have the integral from 2 to infinity of 1 over x times the natural log of x. And remember, this is an improper integral, and so we need to rewrite it as a limit. We need to take the limit as t approaches infinity. This is from section, again, 3.7, and this goes from 2 to t of 1 over x times the natural log of x. All right, so we've had a lot of practice with integrals now. How do we evaluate this integral? What test are we going to use? What integral method are we going to use? Are we going to use the U-sub, integration by parts, trig substitution, partial fractions? What do you think? And hopefully what you're thinking is you're thinking U substitution. And if you thought that, you're exactly right. We're going to let U be the natural log of x, because we recognize that the derivative of that is 1 over x. And we have the 1 over x right here, so that makes things perfect. And so when we go to rewrite this, we're going to have the limit as t approaches infinity. We have 1 over x times the natural log of x, which is u, times dx, and dx is going to be x times du. This is x times du. Of course, the way we did u substitution, because we know these x's are going to cancel, and so we also need to change our limits. Since u is equal to the ln of x, that means our lower limit is now going to be the ln of 2, and our upper limit is going to be the ln of t. And so this is going to be, just clean it up a little bit real quick. The integral from ln of 2 to ln of t of 1 over u du. And we know that that becomes the natural log of the absolute value of u and then we just plug in our limits of integration. So we have the limit as t approaches infinity, and we have the natural log of the absolute value of natural log 2, or excuse me, t goes first, t minus the natural log of the absolute value of the natural log of 2. And when t approaches infinity, this first term well, the natural log of infinity is infinity, and the natural, so this goes to infinity. And so that means this entire integral is equal to infinity. So does it converge or diverge? It diverges. And remember what the theorem said. The theorem said that if the integral diverges, then the series also diverges. So since this integral diverged, that means we can say so the sum, the series, n equals 1, not 1, n equals 2 to infinity of 1 over n times the natural log of n diverges by what test? You have to explain why, remember, by the integral test. All right, so I'm going to go ahead and stop this video right there. I would like you on your own to try part B. I will post the solution for part B. It's a very similar problem. Make sure that you do your requirements ahead of time. All three of those things have to be satisfied. And if they are satisfied, then you can go ahead and proceed with the integral test. All right, see you in the next video. Thank you.